In this video, I'm going to introduce some common topics in the study of crystalline solids for an introductory chemistry audience. So we'll call this, first of all, we won't use a red pen, we'll use a black one. So let's call this topics related to crystalline solids. Okay, and the first topic I'd like to look at is Bragg's law. Bragg's law. Okay, so this is a common topic in an introductory chemistry class, so let's have a look. Just scroll down a little bit. Okay, so imagine you have a crystalline solid. So I'll represent the crystalline solid where each dot represents an atom, all neatly arranged, nicely arranged because it's a crystalline solid. So a repeating array. Okay, and then imagine, I'll change color, imagine that we have incident X-rays. So we're going to try and probe the surface of this crystalline solid with X-rays. So let's say we have let's say we have X-rays coming in a reasonably straight line. Okay, so we have X-rays coming in a reasonably straight line and hitting the surface of the crystalline solid and then bouncing off essentially. And then we have X-rays parallel that penetrate the first layer. Okay, so they penetrate the first layer. Let's zoom in a little bit so we can see what's happening between those two layers. So if I zoom in a little bit, and then I'm interested in the separation of these layers. So let the separation of these layers be a distance d. Okay. Let's drop a right angle from the first X-ray. Let's call this X-ray 1. Let's call this 2. Let's drop a right angle, and we can also do it the same here. And then we're interested, or we can label at least these angles here. So this angle and this angle, which we'll call theta. Okay, so we have angles theta. That means that we have a distance between here and here that we'll call A, and a distance between here and here, which should be exactly the same, we'll call A. So let's make some remarks about this diagram. So here's some remarks. And I should have pointed out that these are X-rays. Okay, so we can remark that X-ray 2 must travel a distance of 2A, so that's this A plus this A, further than X-ray 1 in order to stay in phase. Why is staying in phase important? Well, if we want to detect, this information, detection is going to be possible if X-rays are in phase. So to learn something about what the X-rays encountered along their travel, they have to be in phase, otherwise you lose information with the phase decoherence, etc. Okay, so if you can imagine when the wave is traveling this way, the wave is oscillating, the X-ray oscillating, oscillating, oscillating. And originally it's in phase, so peaks and troughs are at the same spot. Then as this keeps going, this has to travel further to keep up and stay in phase with it. So that's what I mean by it has to travel a bit further. Okay, so far so good. Let's expand upon that triangle. That triangle is pretty small, but let's expand the triangle. A little bit so we can see what's going on. Okay, so we have a right triangle. So I'm looking, for example, at this triangle here. We're just going to translate it down here. We have an angle theta. And if we look at this and apply Pythagoras' theorem, well, first of all, we know that this long length is d. Well, d here is the hypotenuse. We've got an angle here, so this side opposite the angle, which we know is a length a, well, that's our opposite. And the other side, that's not the hypotenuse and not the opposite, that must be adjacent. So we've got the hypotenuse, the opposite, the adjacent. We've got the length d, we've got the length a, and we've got an angle theta. So I know from my mathematics that sine theta is the opposite over the hypotenuse, which in this case is going to be a over d, because my opposite is a and my hypotenuse is d. And I can cross multiply that. This implies, if I bring d up to the other side, this implies that d sine theta is equal to our distance a. Well, I didn't just travel a further, I traveled 2a. So if a is d sine theta, therefore twice a is twice d sine theta. Okay, twice a therefore is twice d sine theta. Okay, so if we look at this equation so far, this is the extra length traveled, right? So this is the extra length traveled in order to stay in phase. Okay, now this occurs for one layer of one crystal layer. For one layer. Okay. We can say one atomic layer, I guess. So we can say, if we can therefore have multiple atomic layers, on this case n equals 1. So then we can confirm that, let's get the eraser. Don't know why I'm writing in a red pen, but I don't want to go and change it to black now. So let's stick with in red what we have, and let's just go to black and pretend we were always in black. Okay, thus per layer, or per atomic layer, there is a whole number of wavelengths. It has to be a whole number because anything less you'd have interference patterns that would slowly over time lose the phase of the two X-rays. So we need a whole number of wavelengths equal to that extra distance, which is equal to 2d sine theta. So this is Bragg's law. It's often used on assessments in introductory chemistry classes, general chemistry, that type of thing. So I would highly recommend that you memorize that equation. Again, the key link here is the link between n lambda and 2a. Remember that 2a is the extra distance traveled here, the extra distance traveled. And obviously, if the wavelengths are in the same phase here and here, they must also, you must have a whole number of wavelengths in the interim, otherwise your previous statements will be invalid. Okay, so that's Bragg's law. Let's go on to look at a Bragg's law calculation. Okay. So let's have a look at a Bragg's law question. So I'm going to call this typical Bragg's law question. Probably more than one. Okay, so question 1. An incident X-ray. So an incident X-ray of wavelength lambda equal to 154 picometer hits, for want of a better word, hits the surface of an iron crystal. And produces and reflects at an angle theta equals 32.6 degrees. Per atomic layer, calculate the separation between atomic layers. between atoms of iron. Okay, so that's a typical Bragg's law type question. So we have to calculate the separation distance d. So we've got our Bragg's law, so we can say that n lambda is 2d sine theta. And I need to calculate d, so I can write that d is equal to n lambda divided by 2 sine theta. Okay. Scroll down. Okay, let's keep the question in view though. Scroll down to keep the question in view. So I've got D, the separation of layers, is n is 1 because per atomic layer, so it's 1 multiple of the wavelength, which is 154 picometer. And then we divide that by the number 2 and then sine of the angle 32.6. Okay, we're going to get units in picometer, and this should give us 143 picometer. So recall the pico is 10 to the negative 12. So recall the pico is 10 to the negative 12. Okay, so that's a typical Bragg's law type question. Do I have any more typical Bragg type questions up my sleeve? Yes, I do. Let's just do a couple more. Plenty of room there. All right, so let's have a look at a second question. So let's call this question 2. The separation of molybdenum atoms in a crystal 157 picometer. Determine the angle. Determine the angle of the incident X-rays of wavelength equal to 154 picometer. And we're told in this question just to assume n equals 1. And typically at the introductory level you can always assume n equals 1. Okay. So the answer to this question, answer 2. Okay, again we know it's Bragg's law. It's got all the hallmarks of Bragg's law. 2d sine theta. Here I need the angle, so I'm going to isolate sine theta. So I've got sine theta is n lambda over 2d, which is 1 lot of 154 picometer. Divide that by the number 2, and then d, which I'm told is 157 picometer. So this is just 154, the units all cancel, divided by twice 157, which is 314, which is 0.4904. And that's sine theta, so theta is the inverse argument of sine of 0.4904, and this is 29.4 degrees. Okay, so that'll be enough for Bragg's law. So let's proceed to look at some crystal structures. So at the introductory level, there's typically three common types of crystalline structures. So we've seen how we might probe those crystal structures using Bragg's law, but what are the crystal structures themselves? So there's three common types that are common in questions. Okay, there is simple cubic, which we will call SC. There is body-centered cubic, which we'll call BCC. And there is face-centered cubic, which we'll call FCC. So these are the three that I would recommend that you focus on. Okay. Now, drawing these is easier said than done, but knowing only how to accept the challenge, I will do my best. So let's have a look at SC. So if you imagine we just have four, so these represent atoms. We just have four of them like that. And then I could superimpose this on yeah, I told you this was harder to do than to say. Okay, so let's see if I can make this look three-dimensionally-ish. That's not too bad. So I've only shown in the red, I've only shown four spheres. That's the face of a three-dimensional cube, which I've shown in black. So you could imagine there's basically another four red spheres at the back side of this cube. And that's basically the packing in a simple cubic structure. So there's two facts that we need to know about simple cubic other than the diagram. So I would say we need to know the diagram. Probably you won't be expected to draw it, but you probably could or possibly could be asked to interpret what's the packing structure in this visual. Okay. So I would suggest that you know what the diagram looks like. Definitely the number of atoms per unit cell. Incidentally, this would be a unit cell. So the diagram is of a unit cell. What's a unit cell? A unit cell is just the brick that you can ultimately build the wall out of. And the wall is typically just the crystal structure itself, or crystalline structure. Okay, number of atoms per unit cell. So it gives information about the packing density. So as we can see, in 2 dimensions, we've got a quarter of an atom here from each side, and 4 quarters is 1. So we've got 1 atom per unit cell for SCC. And we want to know the edge length of the unit cell. So the edge length, I'm going to call that L of the unit cell. And we can see here that the edge length, we've got a half here and another half. And it looks like that's twice the radius. So we've got L is twice the radius. Okay, so these are the facts I would know about SC moving forward. Okay, so let us continue that. BC. In fact, why don't I'll do it and then I'll summarize it. How about that? So body-centered cubic. Maybe I can make this smaller. Actually, it's much harder to draw if it's smaller. But let's see. So BCC, if I had to draw that, I would probably opt to draw the cube first and then put the red spheres in. So if we imagine a 3-dimensional, well, a cube, I guess we don't have to say 3-dimensional if we say cube. There's only one type of cube. So if you imagine that's our cube, it's a reasonable cube, and then we try and add, obviously, one right in the center. So there's a sphere right in the center of the cube, and then we'll put one on this corner. Now these cubes ideally are touching. I guess my problem is I didn't draw my first cube big enough. That was the problem. So essentially I've got one centered at this point, I've got one in the middle, and I've got another one centered at this point going diagonally across the cube. Then I'll have another one here, supposed to be touching that one, centered here. So you can see it kind of slices through the middle of the cube. So from this point to this point, if you could get the cube, so essentially, if I drew the cube again, I guess what I'm trying to show is, if that's the cube, in fact I don't even need the cube, I just need the top of the cube. So if we imagine just the top of the cube here, then I'm effectively slicing through it that way. So imagine you're slicing through it that way and going right down. Okay. So what facts do we need to know about body-centered cubic? Well, we've got not only the 4 corners to give us 1 atom per unit cell, we've also got one in the middle. So we have 2 atoms per unit cell. So 2 atoms per unit cell. We've got the diagram, 2 atoms per unit cell. And then the length is 4 times the radius over √3. you can use geometry to prove this. It tends to be tedious. I tend not to bother showing my students anymore. But you can do it if you're interested. But we have 4 times the radius over root 3. And then finally, the third structure, and then we'll try some calculations, is face-centered cubic. So face-centered cubic is a little bit easier to draw. I'm just going to draw one face of the cube, so I'm just going to draw a square. Okay. And I've got one on the corner, I've got one in the middle of the face, and then one on the other corner. Ideally, imagine they're all the same size. And then I've got one here. So I've just got, whereas this was a slice through the middle of the cube, and these should all be touching if you can use a liberal amount of imagination here. But rather than a slice through diagonally through the cube, we just have one face of the cube. Okay, so every face has a half. I've got 6 halves, which is 3, plus the 4 corners in 3 dimensions is an extra 1. So in total, I have 4 atoms P in its cell. 4 atoms P in its cell, and my edge length here is 4 times the radius over root 2. 4 times the radius over root 2. So if I could summarize this, maybe I can summarize it on the same page. Nope, let's summarize it here. So to summarize, we've got unit cell, we've got number of atoms P in its cell, and we've got edge length L of unit cell. Then I've got simple cubic, body-centered cubic, face-centered cubic, and I have 1 twice R, 2 4R over root 3, and 4 4R over root 2. I would strongly encourage you to memorize this information. It's always hit and miss whether this is information that you might be provided with on a reasonable assessment. Okay, so let's try and do, like we did with Bragg's law, we'll do a typical type of calculation and see what happens. Okay, so I'm going to find a question for us to do. Yeah, how about this one? So let's scroll down. So here's a typical question. Let's call it question 1. Chromium has a BCC unit cell upon crystallization. If the radius of a chromium atom, is 125 picometer, calculate the density of solid chromium in units of gram per centimeter cubed. Alright, so that's a typical type of question. So let's look at a way that you might approach this solution. Okay, so all the clues obviously are in the question. We need to calculate the density. So we know that density is mass per unit volume. So I need to calculate the mass, I need to calculate the volume, and then take the ratio of both. I'm told that it crystallizes with a body-centered cubic structure. So that tells me indirectly there are 2 atoms per unit cell. Okay. So it doesn't matter which you do first, mass or volume. Let's go for mass. So let's look at the mass of chromium. So we'll do a dimensional analysis type problem, type solution here. So I need grams of chromium, so I need my periodic table. I look at my periodic table and I can see that the atomic mass of chromium is 52 grams even, and I set that equal to a mole of chromium. So 1 mole of chromium. My mole of chromium comes up to the left and I cancel the unit. I know that a mole of chromium by definition is Avogadro's number of chromium. So 6.022 by 10 to the 23 atoms of chromium. So that's just the definition. So I can promote the unit atoms of chromium. And because it's BCC, I know that there's 2 chromium in a unit cell. And so I would promote unit cell here. How many unit cells? Well, remember that density is an intensive property. So it doesn't matter how many unit cells, I'll still get the same mass per unit cell. I just have multiples that would scale down for how many unit cells I have. So in 1 unit cell, I can just assume I have 1 unit cell, again, because density is intensive. So let's run the numbers through, and we get 1.727 by 10 to the negative 22 grams of chromium. Alright, so we've got part of our answer. Let's have a look at the volume. Well, I know the volume is just the length cubed. So we take our unit cell, and it has length 4 times the radius over root 3, because it's a body-centered cubic unit cell. Okay. I know the volume is length cubed. So this is just the number 4. The radius, now the radius is actually given to us in the question, right? Let's have a look. What are we given in the question? Yeah, we're given the radius as 125 picometer. So I wasn't sure if we had the radius or the diameter. So we have 125 picometer. So 125 picometer. Now we need to convert that to meter, don't we? Well, actually, no, we need to convert that centimeter, I beg your pardon. So let's do a little bit of dimensional analysis here. So that's our input, but we need to convert those units. So I know that 1 by 10 to the 12 picometer is equal to 1 meter. So that gets rid of my picometer. And finally, I know that a meter is 100 centimeter. So I can cancel meter here. Okay. So that's 4 times the radius divided by, where the radius is in centimeter, divided by root 3, which is just a number that you can hit on your calculator. But now I've got to cube the whole thing, because that without the cube is just L, but I need L cubed, so I need to cube the whole thing. So this should give me a volume of 2.41 by 10 to the negative 23 centimeter cubed. So the density of this chromium is the mass over volume, which is 1.727 by 10 to the negative 22 grams, divided by 2.41 by 10 to the negative 23 centimeter cubed, which is approximately 7.17 gram per centimeter cubed. Okay, so that's a typical type of question. We should probably look at maybe one more. So let's have a look. Let's look at one more. So in that last one, we got density. Let's look at one where we're actually given density and we have to calculate something else. So let me find, yeah, let's look at this one. So let's look at a second question. And this will probably be our last question. So this question is a rhodium question. Density of rhodium, which has the symbol RH, is 12.41 gram per centimeter cubed. Rhodium crystallizes with a face-centered cubic unit cell. Calculate the radius of the chromium atom. Calculate the radius of a, rhodium atom, not chromium. Okay. Okay, so let's see what we know. Well, we know it's FCC, face-centered cubic. So we know there's 4 atoms per unit cell. We also know that the edge length is 4 times the radius over root 2. Okay, so we've got immediate access to the radius, because therefore the radius is the length times by root 2 divided by 4. Okay. Okay, so let's scroll up. So what I need to do first, we need to calculate the mass per unit cell. Okay, so I've got the density. I want the volume. So essentially, to get the radius, I need the length. To get the length, I need the volume. So therefore, I need the mass. I need the mass per unit cell. Okay, so that's my strategy. Okay, so we can do mass of rhodium. It's going to be a dimensional analysis calculation like we saw earlier. So I want gram of rhodium. I look at the periodic table and I can see 102.91 gram of rhodium in a mole of rhodium. So mole of rhodium comes up here. The unit cancels. I know that a mole of rhodium is Avogadro's number of rhodium atoms. So I can promote rhodium atoms up here. It crystallizes with a face-centered cubic unit cell. So there's 4 rhodium atoms in a unit cell. And I'm interested in just 1 unit cell. Multiply that through and we get 6.836 by 10 to the negative 22nd power grams of rhodium. Okay, so I've got the mass of rhodium in a unit cell. Let's look at the volume of rhodium in a unit cell. Well, the volume is just the mass over the density. I was given the density, I now have the mass. So the mass I calculated is 6.836 by 10 to the negative 22 gram of rhodium. And now I can use my density. I know that gram of rhodium has to go down here, and my density gives me 12.41 gram of rhodium, and that's equal to 1 centimeter cubed of rhodium sample. So that gives me a volume in centimeter cubed, which is 5.508 by 10 to the negative 23 cubic centimeters of rhodium. Alright, we're cooking. So now if I go down a little bit further, I can now just cube root it, to get the length. So length is the volume cube rooted. So that's our length, 5.508 by 10 to the negative 23rd centimeter cubed. Let's cube root that. And that equals 3.805 by 10 to the negative 8 centimeter, because we cube root the unit also. Okay. Okay, so closing in, we just need now to calculate the radius. So we said earlier that, actually, what did we say? Yeah, it's face-centered cubic, right? So we know that length is 4 times the radius over root 2. So this is actually equal to, the way I've done it at least, you don't have to do it this way, you can just directly plug in 4 times the radius over root 2. which actually we'll just go ahead and do. I was going to change it, but I'll just keep it like this. So the radius we said was the length root 2 over 4, which is 3.805 by 10 to the negative 8 centimeter, multiplied by the number root 2 divided by the number 4. Alright, so that should finally give us radius is 1.345 by 10 to the negative 8 centimeter, but we need to express this in picometer. So let's use some dimensional analysis, get it out with that inappropriate unit centimeter. I know that there's 1 by 10 to the 10 picometer equal to 1 centimeter. So this finally gives me 1.345 by 10 to the 2 picometer, or 134.5 picometer. Okay, so that's the second example, and more examples would just be more of the same thing. So typically you're either going to be given a length and ask for the density, or you're going to be given the density and ask for the mass, or something like that. So in short, make sure, again, my recommendation, at least to my students, is I would memorize that information. So I would recommend that this information is memorized. So I would say memorize this table. Okay, and that will conclude this video.